All right, so chapter 19 was a pretty short chapter. We started out by looking at carboxylic acids and asking about their acidity, really. How acidic are they? How do different groups impact their acidity? Which was kind of a reboot of chapter 2. We talked about how resonance impacted acidity. We talked about how induction impacted acidity. So to kind of finish up the chapter, let's look at this example right here. We have 3 different carboxylic acids. Which one is most acidic? So pause the video, think about that on your own. Think about what kind of force could impact that, and then restart it. So all of these, I guess if we take a step back, how do we qualitatively look at acid strength? We evaluate the stability of the conjugate base. So all 3 of these conjugate bases are going to be O minus. So we have the carboxylates that we are comparing their stability. And all of these 3 carboxylates have resonance delocalization of that negative charge. So that is identical across all 3 structures. The difference is we have an SH versus an OH versus just the hydrogen by itself. So how are these going to impact the stability of these anions? And what we've talked about a lot is having opposite charges next to each other is a stabilizing force. So how does a sulfur or an oxygen do that? Well, oxygen is more electronegative than carbon, so it's going to be pulling electron density toward itself from this carbon atom, making itself partially minus, making that carbon partially positive. That partial positive is transmitted down the backbone of this carbon chain, so we're going to have a partial positive in that position as well, and that partial positive is going to allow these oxygens to delocalize a little bit of that negative charge to that carbon, which is a stabilizing force for the molecule. So this is called the inductive effect, and that's what stabilizes this conjugate base. So this conjugate base is the most stable. So if that conjugate base is the most stable, then that precursor, so the acid that produced that conjugate base, is the most acidic. So that was just kind of a recap of one way that we can evaluate acidity of different molecules. The second part of the chapter really dealt with how can we separate molecules. And we separate them by making them ions in some cases, and the ions are soluble in water, where the neutral species are soluble in organic solvents. We saw that amino acids, we can't do this. Amino acids will always be charged. But we don't have an amine on any of these, so we should be able to separate them. So how would we do that? This species here is the carboxylic acid that has an acidic proton, so the pKa of this proton is 5. So if we treat this species with an aqueous base, so we'll just write aqueous base, it will be able to deprotonate that OH, but all the hydrogens on this species are not very acidic. They're all CH bonds, and none are acidic. So when we treat with a weak aqueous base, so we could use sodium bicarbonate here, it's going to deprotonate this molecule, and this one's going to remain the same. And just to make sure we fully understand this, what does that aqueous base mean? Well, that could again be this bicarbonate base. It would deprotonate that, making the conjugate acid carbonic acid here. So this would allow us to separate these two. This is going to be aqueous soluble, and this is organic soluble. So what about our other 2 examples? So one example was we had this carboxylate and sodium chloride. Can we separate these two species? Well, we know that sodium chloride is always ionic. It's always going to be aqueous soluble. So this is aqueous soluble. This carboxylate is also anionic at this point, which means it's also going to be aqueous soluble. Sodium chloride, no matter how acidic water is, it's not going to protonate that chloride because it's so stable by itself. But a carboxylic acid can be protonated in aqueous media. So if we have aqueous acid, so in the case above we added aqueous base, this time we're going to add aqueous acid. And what is aqueous acid? Aqueous acid is H3O+. The pK of that is one that we learned before. It's negative 1.7. This is going to donate a proton to this oxygen. If we want to say it kind of the opposite way, this oxygen is going to donate a lone pair and grab a proton from that H3O+. That's going to make H2O, the carboxylic acid, and sodium chloride will not have changed at all. It's still going to be the same. So this, though, is now going to be organic soluble. So we can now separate the organic soluble species from the aqueous soluble species. So essentially what we're doing when we use extraction as a technique is we are separating things based on their solubility differences, which is pretty much always due to their acidity or basicity. So the next question uses a new type of acid. We have the same carboxylic acid. Again, this is on the bottom of page 8. And we have methyl sulfonic acid. We said methyl sulfonic acid was really acidic. We defined the pKa previously. I think it's like -5, -6, something like that. So we'll just say the pKa is negative, I don't know, we'll say 4 to 7, negative 4 to 7, somewhere around there. So both of these are neutral species right now, but if we add water to this, what's going to happen? Well, we know that this OH is really acidic. Water is basic enough to pull that proton off. If water does that, we're going to have this species here that is unchanged. We're going to have H3O+, which resulted from this oxygen donating a lone pair, taking that proton, electrons going to that oxygen there, and we're also going to have the anion of the methane sulfonic acid. So these started out being neutral species. They would both be soluble in organic solvents at that point. Now we have the neutral carboxylic acid, which is organic soluble, and we have the anionic sulfonic acid, which is going to be aqueous soluble. And it turns out that sulfonic acid is so acidic that no matter what we have in an aqueous solution, it's always going to be in this anionic form. So no matter what we have, if we had aqueous acid, so if I said H3O+ / H2O, there's still some water around, and that water is going to be basic enough to deprotonate that sulfonic acid. So just note that anytime we have an aqueous solution, this is always going to be anionic, which means it's always going to be in the aqueous layer. And then we can separate it from things like carboxylic acids. Yeah, and I'm going to do one more example to incorporate an amine, because we haven't done that yet, and I want to do that. So what about an amine? So say we had something like a mixture of this molecule with, and we'll go back to one we just talked about, this molecule here. These are both neutral right now. They're both going to be organic soluble, but we should be able to separate them. What have we done previously? We've either protonated or deprotonated a carboxylic acid. It turns out that amines, and we've already seen this even in the last chapter that we talked about, we saw amines were basic. They reacted with Lewis acids. They also react with protic acids like H3O+. So if we added aqueous acid to this, aqueous acid is going to be this H3O+, that has a pKa of negative 1.7, as we just said. This amine is going to deprotonate that aqueous acid to make the quaternary ammonium salt, water, and this ester is going to remain unchanged. The ester is not very basic. It's not very acidic. This is basic, but not very acidic. So it will deprotonate that, and we can say, oh, what side is the equilibrium going to be on? Well, if we look at the pKa of NH4+, one that we've looked at quite a few times before, NH4+ is 9. This is going to be really close to that. It's a nitrogen with 4 bonds, 1, 2, 3, 4. This is a nitrogen with 4 bonds, so it's going to have a similar pKa. So that tells us that once we add our aqueous acid, the equilibrium is going to come over here, where we're going to have an aqueous soluble quaternary amine salt, and we'll put that with the water, I guess. And then we have an organic soluble neutral molecule. So again, we can essentially separate amines by protonating them with aqueous acid. We can separate carboxylic acids by protonating or deprotonating them. We saw sulfonic acids are always in the anionic form. So using extraction is another technique that we can use to separate molecules based on their acidity or their basicity. So let me know if you guys have questions about this kind of stuff, and we will talk about it then.